Alright, this is note card number 8, which is on average rate of change, or as we've been calling it, AROC. Now remember, we started the class with the example of a roller coaster, and so we had some roller coaster where you were going up, and then some top part of the roller coaster, and then you were going to go down the roller coaster fairly steep. And we had this idea that there was going to be a camera taking a photo of people right as they passed here. And so it would be nice to know how fast they were going at that point, or their instantaneous speed. But we didn't know what the instantaneous speed was, and so we were going to estimate it by taking points around that yellow line and finding the slope between the points, and then using that as an estimate for the instantaneous speed. So we're basically taking this orange line, which is the average speed, and using that to estimate the instantaneous speed. Now, to get a better estimate, what we talked about was moving those points closer together, and that would give us a better estimate for the instantaneous speed. So if we move those points really close to the yellow point, we get a really good estimate for the speed at that yellow point. So moving those two orange points closer and closer together is going to give us a better estimate of the instantaneous rate of change, or the instantaneous speed. And so we're going to go back to that idea in this note card. We're going to start in AROC, and as we go toward note card number 9, we're going to start talking about IROC. So this note card is about AROC. The only problem where we're going to see anything about instantaneous rate of change, or IROC, is in this last problem down here. So, but I want you to kind of hold this idea in your mind as we do some average rate of change problems, and then as we go into note card number 9, we'll talk more about instantaneous rate of change. Alright, so average rate of change is just the slope, and so the first equation we see here is just a slope equation. And this is the slope between 2 points. So this is slope between 2 points. And you've been using this equation for a long time, since Algebra 1 probably. So that's the slope between 2 points. And as we just looked at, that's the slope of a secant line. Number 3 has 2 equations in it, and we're not going to spend much time on the note card video looking at what these equations mean. In class, we will try to use Desmos to explore these 2 equations, and hopefully you can get a better sense of what they are. Basically, this equation is the slope between a point, and that point would be a comma f of a. So it's the slope between a point a comma f of a and any other point on f of x. Okay, so this is kind of a more general equation that's the slope between a and any other point, whereas this one is the slope between the point a and just one other point, b. So they're a little different in that sense. And then this equation over here is the slope between point A and a point that is close to A, but it is h away. And the reason it's defined this way, the reason that this equation for slope is useful, is we're going to be able to adjust we're going to be able to adjust that other point by making h different values. So we have this point A, and then we'll have another point that is h away from A, and we can move that other point by changing the value of h. And eventually we're going to turn the value of h, we're going to bring it closer and closer to 0, and we're going to see that secant line turn into a tangent line. So that's the big transition from average rate of change to instantaneous rate of change. Alright, but for right now, let's just focus on average rate of change. And look at question number 1. It says, in an experiment of population of bacteria, find the average rate of change from P to Q and draw the secant line. So the secant line is just the point that goes through those two, or the line that goes through those 2 points. And the slope of that line, the slope of that secant line is the average rate of change. And so we're just going to use y2, which is 340, minus y1, which is 150, divided by x2 minus x1. And that's going to give us 190 over 22, which is approximately 8.64. And then the units of that are bacteria per day. So the average rate of change of bacteria is that there are going to be a new 8.64 bacteria per day in that time interval from the 23rd day to the 45th day. So that's an average rate of change. Number 2, this one talks about traffic flow. In the first one, we're given a graph. So that's the way that they represent the equation in the first question. In the second question, we're given an equation. And then in the third question, you can see that we're given a table. So lots of different representations of functions here. Number 2 deals with traffic flow, and we're asked to find the average rate of change of the traffic flow from 10 to 15 minutes. So this gives us the traffic flow over a 30-minute period. And we're just going to do the same thing. We're going to find the slope. So we need to know what f of 10 and f of 15 are. And so you can use your calculator here. It tells us we can use our calculators. And so if you're in radian mode, you should have gotten f of 10 was 78.164, f of 15 is 85.752, and AP, when we're doing free response questions, is going to want 3 decimal places, so let's just get in the habit of using 3 decimal places there. And then we're going to do the slope of that. So 85.752 minus 78.164 divided by 15 minus 10. And when you go through that calculation, you should get 1. I'm going to get rid of this here. The final answer would be 1.518. And then the units of that are cars per minute. So there's an increase in the traffic flow over that time interval. Again, that's an average rate of change. Number 3, this one's a table. It says use the table below where f of t is a population and t is a time to estimate f prime of 1870. Now, we haven't seen this notation before. That little apostrophe thing, the way you're going to read that is f prime of 1870. And what that prime represents is an instantaneous rate of change. So what they're saying is this population starts out in 1850 at 23.1 million. In 1860 it grows a little bit to 31.4 million. Then it's at 38.6 million, and then it goes up to 50.2 million. And we don't know exactly how that population is growing, but we know that it's definitely not linear. So it's some function that looks like that. We're not given an equation, so we don't know exactly what it looks like. But what they're asking us to figure out is what is the instantaneous rate of change, which is the tangent line, in 1870. Now, we have no way of figuring that out. So we have to estimate it, and that's why it says estimate f prime of 1870. So the way that we're going to estimate it is by taking this point and and finding an average rate of change between those 2 points. That's going to give us probably a pretty good estimate for the instantaneous rate of change in 1870. So the y values are the populations, so we want to do 50.2 minus 31.4 divided by 1880 minus 1860, and if we do the math there, we should get, I think, 18.8 over 20, which is 0.94 million people per year. So another way to write that would be 940,000 people per year. And that goes some way in our interpretation answer. The meaning of our answer is that the population is growing at, and an estimate for the population growth in 1870 is about 940,000 people per year, but that's just an estimate. So that's the answer to number 3. Notice these are all rates. So the thing I want to point out is we have people per year in this one. We have cars per minute in this one. We have bacteria per day in this one. So this note card and these kinds of questions are just dealing with slope in real-world situations, and we're coming up with rates of change. And now in the next note card, we're going to go and take those average rates of change and turn them into instantaneous rates of change. And they're not going to be just estimates. We're going to use calculus now to figure out the exact rate of change.